Hi everyone, and welcome to another video of the SAFI webinar series. In this video, we are going to have an overview of tapered sections. Tapered sections are sections for which the dimensions vary according to the position of the physical member. Each dimension of the section is interpolated and the corresponding properties are recalculated based on the interpolated dimensions. If the properties of the source sections have been modified by the user, the recalculated properties will be corrected appropriately. To add a tapered section, the user needs to create a non-standard section. Next, we create a section type which will be a variable section, and we associate the sections already created at each segment of the variable section. In addition, the longitudinal profile must be selected. The last step is to assign a section to the member as usual. There are two positioning methods for the section. The first one is the relative, which is a ratio of the length of the member. The second one is absolute, where the user needs to specify the exact position from the start of the member. The interpolation types defines the longitudinal profile of the tapered member. There are three interpolation types, which include linear, quadratic, and cubic. For linear profiles, the user can specify at minimum 2 sections, but it is possible to define more than 2 sections. In this case, the variable section is composed of several linear segments. For quadratic interpolation type, the user needs to select 3 sections. For the cubic interpolation type, it's required to select 4 sections. Let's start our demo. The first step before creating a tapered section is to create the non-standard sections that will be assigned to the variable inertia section. To create a non-standard section, we go to the Tables menu, we select Sections, and then we select Non-Standard Sections. It is also possible to display the Sections toolbar, and we click on the button Non-Standard Sections from this toolbar. We create the first non-standard section, a round section with a diameter of 200 millimeters. I will create another one with 500 millimeters, and I'll create a third one with 800 millimeters for the diameter. After creating the non-standard section, we use the command variable sections on the section toolbar. We can also access this command from the Tables menu, Sections, and then Variable Sections. In this dialog box, the user can specify the method of positioning, so we have a relative position. In this case, the user needs to enter a ratio. 0 will correspond to the first joint of the member, and 1 will be the second joint of the member. For the second option, absolute positions, the user needs to specify the total length of the tapered members. For example, if we specify 2 meters here, the user can specify the position of the sections. The joint I will correspond to the position 0, and the joint J, or the second joint, will correspond to the total length of the member. To create a variable section, we need to assign the non-standard section that we created to the segments of the variable section. Each variable section must have at least 2 segments. We assign the first section to the first segment, and we assign the second section to the second segment. We can click on the button Preview Variable Section to preview the section graphically. We can see the profile of the section, and the user can click along the tapered member to evaluate the properties of the variable section. For example, at 40% of the length of this tapered member, the properties are displayed here. The user can also specify the ratio of the length of the member from here. For example, at 60%, we can display them. This type of interpolation is linear. The section properties are interpolated linearly between the 2 sections that we assign to this variable section. We can also specify a quadratic type of interpolation, so the user needs to specify a third segment. For example, segment 2, it will be positioned at 50% of the length, and the third section will be at the end of this member. We can click Preview. We can now see that the profile of the section changed. For this type of interpolation, we can see the quadratic shape of the profile of the variable section. The last type of interpolation is cubic interpolation. The user will need to specify 4 segments. For the 4th segment, I can specify this section, for example, at the end of the member, and this one, 0.7, and I click Preview Variable Section. Now we can see the cubic shape. For the linear interpolation, the user has the option to add more than 2 segments. In this case, we have 4 segments, and if we click Preview Variable Section, we can see that the section varies linearly between each segment. The last step is to add a name to this section, and we click OK to validate. Let's create a member. To assign the section to the member, we need to edit the attributes of the member by simply double-clicking on this member, and we assign the variable section. We can also change the view to a solid view. By default, variable sections will be displayed as a constant inertia section. We can change the view mode by editing the display option. In the Visibility tab, we select Members, and in the Variable Sections option, we change the constant to Interpolate. We click OK. We can now see the tapered menu view. Now let's open an example. In this example, we have 3 identical beams with the same variable section, and the beams are under the uniform load. The only difference between these 3 beams are the number of divisions. The first beam is composed of one physical member that is divided into 2 members. The second beam is divided into 5 members, and the last beam is divided into 10 members. Let's run the analysis. In the graphical analysis results, we display the bending moment mz. If we compare the results between the beam with 2 divisions and the beam with 5 divisions, we can see there is a big difference in the maximum bending moment mz. We can see a difference of 10% in the results. If we compare the results between the beam with 5 divisions and the beam with 10 divisions, we notice in this case the difference is small, closer to 1%. We can do an example by creating another beam with 20 divisions. So, I select this beam and I use the command copy. I will copy this beam here, and now I select the new beam and I subdivide each member to 2 divisions. The new beam now has 20 divisions. Let's run the analysis again. If we compare the results between the beam with 10 divisions and the beam with 20 divisions, we can see that the difference is even smaller. It's less than 0.4%. To have better results when we have tapered members in the model, it is advised to subdivide the tapered members into many divisions. The number of divisions varies depending on the loading and the complexity of the model. In general, at least 5 divisions are advised. The user can perform this type of sensitivity analysis by varying the number of divisions to find the right number of divisions that needs to be used for each tapered member. Thank you for watching, and catch you in another one of our webinar series videos.